Hello everyone. So last video I had introduced to deep learning and neural networks. We saw how the basic architecture of a neural network looks like and how it works. So in this video we will just brush up the topics and learn more about these neural networks and what they are capable of. So let us just start. So yeah, working we had discussed. So let's say we have this is known as input layer, hidden layer and the output layer of neurons. So let's say we are performing a classification task, then the output layer will, let's say, give the output of 0 or 1. And in a neuron there are two compartments, one which does the weighted addition as shown in the top right here. So we have the values of x1, x2, x3 features which get multiplied by the weights w1, w2, w3, and g is the activation function which is applied along with the bias term w0. So yeah, this way we calculate the output of each neuron and then go forward. We have weights corresponding to each of the connection, and in the forward propagation we just calculate the output by passing the weighted sum through the activation function, and in the backward propagation we just update our weight so as to minimize our loss function. So today we will also see how exactly we are doing that. So yeah, let us just continue. So if we are asked to design some basic logic gates using neural networks, how can we achieve that? So these are quite simple. So let's say we have a single input layer without any hidden layer, we have just output layer. So this would help us to understand how exactly we are able to perform classification tasks, or how exactly we are able to manipulate a data set using neurons to create a decision boundary in and giving us an output. So let's say we want to model the OR gate using neural networks. So you know the truth table of OR looks like this. If any one of the outputs among A and B is, inputs among A and B is, let's say, 1, then the output will be 1. If both are 0, then the output will be 0. So let's say we have to actually take the appropriate weights and do a weighted sum, and let's say we have the step function as the activation function for the output layer. So A or B, let's say A and B are 0, then what is the weighted sum? Will be 0 into 20 plus 0 into 20 minus 10. So a total of it will be minus 10, and if it is a step function, the value of a negative means the output will be 0. And similarly, if any one is 1, then it will be 20 into 1 plus 20 into 0 and minus 10, which gives a total of plus 10, which is again greater than 0, and for the unit step function the output will be 1. And similarly, if both A and B are 1, we can just see that output will be 30, which is again above the threshold of 0. So similarly, we can also denote a XOR gate. So if you plot this in graph, you will see that using one linear boundary you can separate this. So we did not require any hidden layer for this. But a XOR gate, if you see, is not possible to separate even with a linear boundary. So a simple structure like this would not work. We need one more hidden layer for this, and also our weights. So we using these are not the exclusive solution to this. Let's say we may also take some other set of weights and some other set of thresholds which also would do the work of determining the XOR gate. So let's say we take A and B to be 0. So both of these are 0, and then the output of this is 0, 0, and if the threshold is 1, and the output is 0, input is 0, then it is belonging to the low class, and therefore the output will be 0. And here the output will be 1 because the threshold is minus 1 and the input is 0. So so we get a 0 from here and a 1 from here. So if we just do 0 into 1 plus 1 into 1, we get 1 up here. So input to the activation function will be 1 of the final layer. Then the final layer has a threshold of 2. So which is less than 2 and 1 is less than 2, so the output will be 0. So we see that if the input x1 and x2 both are 0, we are getting the output of 0. So yeah, that's how it works. You can check for the other values by taking x1 equals to 0, x2 equals to 1, or x1 equals to 1, x2 equals to 0, or both of them to be 1. So you can just build you just try to build a NAND gate using using uh, using these neural networks. So you can maybe write it in the comments how did you do that. So yeah. So let's see how training neural network would work. So it involves mainly backpropagation, but forward propagation is also a part to calculate the loss, to calculate how much error is there. So the forward propagation involves applying a linear transformation, as we saw here in this. We are applying a linear transformation in the forward propagation, and as well as applying an activation function through the weights and biases to finally get the loss. So the backward propagation involves updating the weights and biases in order to minimize the loss function. The back propagation is, if you see, is really just an application of the chain rule from calculus. It is easiest to understand if we convert this two-layer network into a graph representation, which we are going to see just now. So back propagation algorithm you can find in many neural network books in the internet. It would look really scary, but it is quite simple to understand that if you just see it in this way. So let's say we have layer L1 which contains weights and biases W1 and B1. We are giving an input X, then we are applying an activation function, let's say S, and let's say we have another layer which contains other weights and biases B2 and W2, and which gives us a value after applying an activation function of L. So let's say we calculate the loss function, and we now need to differentiate L with respect to L2. So why we are differentiating? So like partial derivative we are finding to just minimize the weights. So yeah, the slope we generally calculate, and then we apply some optimizing function, let's say gradient descent. So the loss function, the loss L with respect to the previous layer, which, and then this layer is also dependent on the activation function. Then the final loss with respect to S can be written as this due to the chain rule, and then also the final loss function with respect to this layer L1 can also be written as this, and this term dou L by dou S can be replaced by this entire term, and again we need to find the loss. So what we are doing exactly in the back propagation, we are updating the weights and biases, right? So if we want to update weights, let's say the weight W1, if we need to update, we need to see how exactly, and you know how L is dependent on W1, it is just a linear combination. So dou L by dou W1 can be written as dou capital L1 by dou W1 multiplied by dou L by dou capital L1 due to chain rule, and this dou small l by dou capital L1 can be replaced like this. So let's say if you want to update the weight W1, then you have something like this result, and uh, and like a normal function, what you do is you minimize this function. So basically it would not be advisable to directly equate it to 0. You can use some optimization function, let's say this gradient descent, which I have already talked of. So let's say we are trying to update this weight W1. So the new weight W1 will be equals to W1 old weight minus alpha into the slope. So we are just trying to reach the minima. Let's say our loss function L has a minima here, and we are at this level. So our slope here is positive. So the slope with respect to W1 is positive, and hence we need to move backwards. Similarly, the slope here would be negative, and we would be requiring to move forwards. Therefore, this minus sign would always hold true. This I have already explained in the gradient descent. So gradient descent is also an optimization function if you see it in that way. Similarly, you can update weights W1. Similarly, you can update biases. You can update other weights W2 and biases B2. So this was our backpropagation algorithm. Now we have also something known as dropout layer. We temporarily removed unit from a neural network selected at random. This is done to prevent over reliance on certain units and prevent overfitting. So let me tell you a story for this. Let's say we are doing a cat dog classification. We are taking images where we determine that whether the image is of a cat or a dog. So before when I will explain convolutional neural network, I will explain in detail of how it is working. But now let us assume it as a black box and say somehow let's say assume that the model is trying to predict whether the picture is of a cat or dog. So for the model, it knows only the pixels, right? It has only the pixels data. So it was tested that, let's say while training the neural network, if we give some training data as cats and some training data as dogs, and let's say we all of our dogs are lying in some Antarctic region, due to which the background color is white, let's say, or due to some other reason, due to white background or white floor, all our dogs data is white. So basically what it does, the neural networks have in its neurons, it stores an information that white background generally would mean dog, but that is not true, right? So our neural network is becoming over reliant on the background data, and due to some like neurons, it is getting like over dependent on them. So if we give a cat diagram which with a background of white or some appreciable amount of white pixel, it might also say that that diagram is of a dog. So we need to understand that which pixels we need to give more weightage to. Should the background pixel be given more weightage, or should the features of the actual animal be given more weightage? So actually we don't need to give much weightage to any of the pixel. This is why we do this dropout layer. If we have a dropout layer, it randomly drops some units of the neural network, so as to just prevent over reliance on any one network. So one pass of forward pass and back propagation will also done by removing certain units. Then in the next epoch, by epoch I means the number of iterations in which I am updating the weights. So again then we will forget some other set of neurons. We are just making sure we are not becoming over reliant on any particular neuron. So this is the concept of the dropout layer. Now we have some optimizer function. As I explained in the backpropagation, we need some optimizer function to actually minimize our loss and update our weights. So optimizer function is an algorithm or a function that adapts the neural network's attributes like the learning rates and the weights. Hence, it assists in improving the accuracy and reduces the total loss. Some optimizers are, let's say we have stochastic gradient descent, we have batch and mini batch gradient descent, these two I have already talked of. We have stochastic gradient descent with momentum, ADA grad optimizer, we have RMS prop optimizer, we have ADA delta optimizer, which is just an improvement on ADA grad. We also have ADAM optimizer, which is the most famous, and we will generally use it in our projects as an optimizer function. So but let us just, for the sake of knowledge, let us just go through what each of the optimizer function means. So we have stochastic gradient descent. We will just go a quick overview without much information of the math behind it. So this thing is quite simple. I just explained you that we do a derivative of the loss function with respect to w, and then just separate and just subtract it from the old value to get the new value of weight. We are doing the updating the weights in order to reach the minimum. So a small learning rate, this alpha actually determines how big our step would be. So a small step would take a lot of time to reach the minimum. Medium amount will be just right, and a large amount of step might just make our make our life difficult by overshooting the values. So yeah, so in stochastic gradient descent, we just for each data point we do one iteration of updating the weights. So let's say we have stochastic and batch and mini batch. You already know, I am not explaining those. Batch gradient descent, all of the data points at once, it just updates the weights, and mini batch, it just takes few of the data points and then updates the weights accordingly. Then we have stochastic gradient descent with momentum. It is a optimization method that adds a momentum term to the regular stochastic gradient descent formula. So we have the old weight and we are trying to update it. We add just an eta, which is the momentum. So basically you can see, if you have a minima over here, if you have a 3D parabola in which a minima is present in the red dot over here, if you go without momentum, if you will maybe shift and gradually move towards, but with momentum, there is a possibility that you will reach quite earlier. So we also should take care that the momentum should not be too much so as to overshoot that. It should just be able to reduce our time. So it should be a threshold level. We can tune that value. So we can use the momentum as for fine tuning our model to get it more accurate. We also have the ADA gradient descent. So the idea for this is that in our loss function we take care of our weight. So sometimes, as I showed you, that a small learning rate will be taking more time, and a large learning rate can overshoot that. But at times, let's say we know that our minima is, let's say, very far away from us, so we might be requiring to take a large jump now, and as we reach close to the minima, that is, as our slope decreases, magnitude of slope decreases, we might want to just take small steps in order to not overshoot that. And if we start taking small steps initially, we may take a lot of time. So here comes the concept of adaptive learning rate. So we change our learning rate accordingly. So when it is required, our learning rate will be high, and when it is not required much, our learning rate might be some slow. So yeah, we just introduce a term in our loss function for that. The intuition behind AdaGrad is that we can use different learning rates for each and every neuron and for each and every hidden layer based on the different iterations. You need not worry how the exact mathematical formula is coming. You can just use its implementation in the library. So we also just make sure that you understand the concept behind why exactly we are doing some catch value or like this. So the RMS propagation, which is root mean square propagation, is a special version of AdaGrad. So which is a learning rate is an exponential average of the gradient instead of the cumulative sum of squared gradients. The RMS propagation basically combines momentum with AdaGrad. So you can see that this is the formula for this RMS propagation, root mean square propagation. This is also an optimizer function. So these are the old optimizer function which we don't use, and this Adam optimizer is the one we use now. And this Adam optimizer is one of the most popular and famous gradient descent optimization algorithm. It is a method that computes adaptive learning rate for each parameter. So it combines everything what we have talked about. It combines the methods of adaptive learning rate, it combines the methods of gradient descent with momentum. So it stores both decaying average of the past gradient similar to momentum, and also the decaying average of the past squared gradient similar to RMS prop and ADA delta. Thus it combines advantages of both the methods. It combines this momentum thing also and the adaptive learning rate thing also, along with the RMS prop things. So yeah, that's the Adam optimizer, which is most famous, and we will use it in our next video. So next video we are going to talk about a project on, let's say, detecting fake currency in banknotes. So yeah, so I will try to post a video every week from now on. So yeah, we have that, and we will be using the optimizer function. And let's say we have this I found it on towards data science websites to actually see how towards the minima, let's say the star is the minima, how each of the optimizer function is helping to reach the minima and how much time it takes. You can see momentum just have a moment, it tends to have a momentum in the direction into which it is moving, and therefore it overshoots to the farthest value. And similarly for the others, you can see the stochastic gradient descent goes in a very slow manner, because each and every weights it updates every time for each data point. So you can see the red line is moving very slowly. So yeah, and similarly for the others also, let's say NAG have some degree of momentum, that is why some other optimization function, their characteristics are being featured here. So yeah, that's all from this video. So meet you in the next video with a new project, and there we will learn how to apply how to use TensorFlow and to apply a neural network, how to code that out. So till then, thanks a lot.